Let us start lecture 32, and the course is phase diagrams in single component and binary systems. And today's topic will continue our discussion on condensed solution, and we are actually trying to find out Gibbs free energy of mixing, enthalpy of mixing, volume of mixing, as well as entropy of mixing. In the last lecture, we have found out the values of the expression for del H mix, del G mix, which is Gibbs free energy of mixing for the solution formation at a constant temperature and pressure. And then we have extended our discussion. We have found that del H mix goes to 0 as well as del B mix goes to 0. So, now we have to find out del S mix, which is the entropy of mixing due to solution formation. So, today's topic is condensed solution, measurement of del G mix, del H mix, del B mix and del S mix. In fact, in the last lecture for the formation ideal binary solution at constant temperature and pressure, we have seen delta G mix equal to XA in terms of Gibbs free energy for mixing or the partial molar mixing of ith component in the solution, A component as well as B component in the solution. So, XB. Okay. So, it actually turns out to be XA RT ln XA plus XB RT ln XB. Okay. And we have found del H mix equal to 0 as well as del V mix equal to 0. And then we have also seen that del G mix equal to del H mix minus T del S mix. So, since this is 0, so it can be equated to T del S mix. Now, we have to find out del S mix, and remember these are all for 1 mole solution. Now, in order to find del S mix, we can make use of a formula which is delta G equal to V del P minus S dt. This is for closed system and fixed composition, and that time we can write where we keep pressure constant as well as composition constant would be equal to minus S. So, from here this relation, so we have found out one relation delta G mix equal to minus T del S mix, and from here we can get this, we can get this. So, from here we get we can write this, and since XA, XB are constant and R is basically constant, this is universal gas constant. So, then we can write minus XA R ln XA or plus xp r ln xp. So, del S mix, it turns out to be this relation, this. Okay. Now, this is for 1 mole of course, because we are getting X A and X B. So, we can actually write this one can be written as X A del S A bar m plus X B del S B bar m. So, this is also for 1 mole. And hence, we can write equal to minus r ln x a and del S bar m b equal to minus r ln x b. So, these two quantities are basically the partial molar free energy change due to the solution formation of A component and B component. Okay. And now, let us understand the physical significance of it. Okay. In fact, we can understand the physical significance of, so significance of delta G mix, delta H mix, delta V mix and delta S mix, if we try to find out that. So, delta G mix equal to X A X B. So, this is actually we are doing it for A B ideal solution. Fine. Now, here if we consider any composition other than pure condition, so then X A as well as X B would be less than 1 greater than 0. So, if we consider any composition other than pure component. So, if these are negative, so then long term also becomes negative. So, this delta G mix at a particular temperature and pressure is less than 0. It suggests that mixing or solution formation is spontaneous. Now, this can, from here it is less than 0, that is why it becomes spontaneous. But now you have to remember that delta G mix equal to delta H mix minus T del S mix. So, now this is 0 for ideal solution, since we are taking ideal solution. So, that is what delta H mix will not have any contribution to the delta G mix. So, that is what we can easily say that if it is less than 0 for ideal, and this is actually for ideal solution formation, a delta G mix is less than 0 and it becomes spontaneous. Okay. But had it been delta H mix for in case of real solution, it cannot be 0 also. So, it can be either positive or negative, it can be highly positive, it can be highly negative. So, we will see later on when we treat a situation where there will be contribution for the solution formation from enthalpy. So, then we will see that up to a particular situation delta G mix would be less than 0. There could be possibility that delta G mix can become greater than 0. Okay. So, we will not discuss at this moment, but at this moment this condition is substantiated by this particular condition where delta Hmix equal to 0, fine. So, that actually also can be proven from here. So, delta Gmix, or we can say delta Smix equal to minus R xa ln xa plus xb ln xb. So, from here we will get that from here. So, if you see this, this is the one. Okay. Now, if we see this, now xp and xa same condition will be applicable here for the solution formation. So, then this quantity goes to negative. So, actually it becomes positive. Now, if we see delta Gmix equal to minus T del S mix, so this is always a negative, less than 0. Okay. Why? Delta S mix is positive. For the solution formation, delta S mix becomes always positive. So, delta G mix is becoming always negative, because T is in Kelvin. So, that is what any non-zero value of for T, we start from 0 Kelvin and above. So, any non-zero value we will always have delta G mix to be negative. So, that means mixing or solution formation is spontaneous in case of ideal solution. Now, we have seen that delta H mix equal to 0. So, if we try to find out the significance of delta H mix, so that means during solution formation no heat will be evolved or absorbed for the solution formation. But this is not true in case of practical situations, like when we mix KCl. So, this is 0 no, for ideal case, but KCl, if you take KCl salt, sodium potassium chloride salt, and mix it with water, you will see that the surface of that beaker, the glass beaker, it will cool down, and there would be water droplet trickling down on the surface of the glass beaker, where we have formed the solution. So, there actually when you form the solution, you actually you will see the absorption, it is basically endothermic reaction, the temperature drops. So, since the temperature drops, there will be condensation on the surface of the beaker. Okay. So, there it is basically endothermic. So, that means enthalpy contribution will be there for the solution formation. So, similarly, there could be situation, for example, sodium hydroxide, if you mix in a water, you will see that the surface of the beaker will get heated up. So, it is basically exothermic, that solution formation, that is coming due to the enthalpy contribution. So, here it means that there will be no heat evolution or absorption. Okay. And delta Vmix equal to 0, it suggests that there is no volume change. Due to solution formation. So, that means molar volume of both the components A, B would remain same whether you keep them in pure condition or in the solution. Now, this we have seen that delta S mix equal to minus R xa ln xa plus xb ln xb. This can be proven from another route. Okay. So, we know that S entropy is expressed as K, which is the Boltzmann constant, ln omega. Okay. So, K is the Boltzmann constant, and omega is the distribution and this is interesting that distribution is, I can say, distinguishable distribution. Fine. For example, if you take pure metal and if you take only A type atom is there and all the atoms are situated at a correct position in the 3 dimension. So, that time you can only distribute those A atoms in a single way actually. Why? Because let us say you have A atom, this is A and this is A, and both the atoms are identical, whether it is sitting here or here, the distribution would look same. So, it is not distinguished. So, only one way of distinguishable distribution is there. So, that distinguishable distribution suggests that what. So, this omega is that. Okay. So, now W is basically like that, it is not omega. So, you can also write it like this, okay, that distribution part. Now, this way also one can find out the same expression can be found out. So, let me try that. Okay. For that, let us say we are making a solution of AB and at a particular temperature and pressure, and we have taken, instead of moles, we have taken N A number of atoms and N B number of atoms. So, these are basically number of atoms. Fine. We are trying to form a solid solution, let us say both we have started with the solid. Okay. So, we are trying to form solid solution. Fine. So, and these two numbers are chosen in such a fashion that Na plus Nb, that gives me a number which is Avogadro number. And it hence when I make a solution, it is basically 1 mole solution, 1 mole mix or mixture or solution or homogeneous mixture or solution. Fine. So, if that is the situation, this W can be written as, which is the number of distinguishable distribution. So, this NV factorial of NB and factorial of Na and factorial of Nb. Okay. So, this way one can write this distribution. We can also write it like this: Na plus Nb factorial and Na factorial and Nb factorial. Use this particular formula here, del S mix. Okay. So, this del S mix is basically nothing but entropy of solution minus entropy of pure A and entropy of minus entropy of pure B. Okay. So, this is the thing. Now, this is for solution. Similarly, I can write omega for pure A, which can be written as 1, which will be 1. So, I can write K, which is the Boltzmann constant, ln omega solution minus K ln 1 minus K ln 1. So, it actually turns out that fine. So, from here I can write K ln Na plus Nb factorial of Na plus Nb factorial of Na and factorial of B. Now, from here, now I will use Stirling approximation. Which says ln factorial of any quantity, let us say Na plus Nb factorial. So, that becomes fine. So, I can use this one. So, del S mix equal to K Na plus Nb ln minus plus. So, this two quantities goes to 0. So, now we can write Na. So, this particular thing Na, which will be minus Na plus will be minus Na and minus Nb ln Nb minus Nb. Okay. So, we can write this. So, then become K Na plus Nb ln. So, this two quantities would get cancelled, Na and Nb, if you take this thing out from the bracket. So, then we are left with and fine. So, then I can write, I can take a minus out. So, let me just keep it like this, minus K. Then you will see that Na ln Na divided by Na plus Nb plus Nb ln Nb divided by Na plus Nb. Okay. So, now I will take out, I will just multiply Na plus Nb here, and hence it will be, and this quantity, since Na by Na plus Nb is nothing but Na divided by Nv, Avogadro number, so which is nothing but Xa, mole fraction. Okay. Similarly, Nb divided by Nb plus Na plus Nb is nothing but Nb divided by Nv equal to Xb. So, I can write this one as Xa and this one is Nb divided by Na plus Nb ln Xb. So, finally, we see that minus K Nv, and this again becomes Xa ln Xa plus Xb ln Xb. And now we K into K Nv Avogadro number is nothing but universal gas constant. So, I can write equal to minus R Xa ln Xa plus Xb ln Xb. Okay. So, we see that the similar formula we are getting whether we go through del Gmix route or whether we go through using this formula. Using this formula, okay, we are getting the same formula, same expression for del S mix. Okay. So, let me stop here. Now, we will start getting into the graphical way of representing these four quantities, del G mix, del H mix, rather three quantities, not we will not deal with del V mix, del G mix, del S mix as well as del H mix, and then we will try to find out a situation where whether we can actually express free energy of the solution over the entire composition range considering Xa equal to 1 to Xb equal to 1. So, that means pure A to pure B, how the curves look like. Okay. So, that particular understanding will lead to calculation of isomorphous phase diagram in case of ideal mixing consideration. So, let me stop here. Thank you very much.